Thank you very much. Thanks for being here. Thanks for the organizer for this nice conference. Yes, I'm going to talk about, yes, that's better. Exponential ergodicity for geophysical fluid model for geophysical fluid dynamics. That's GFD there. So this is on an ongoing project. What we want to study is effectively, when we study ergodic properties, we want to understand the long time average behavior and the subject of a model. And our model of interest is a model for the ocean and the atmosphere dynamics. And in our case, we consider it subject to a random perturbation on one of the two layers. So we are considering a layered model. I'm going to be more precise in a second. And why we want to do this, and with this configuration of forcing, is to better understand the influence of stochastic wind forcing, for example, on the surface of the ocean, and to ensure the quote-unquote good behavior of model on the climate scale. This is when we consider long-time average behavior. And how we're going to do this? We're going to do it from a mathematical perspective. So you're just studying its ergodic properties, as I said. So this is a joint work with Joachim Brocke and Tobias Kuna that you heard from yesterday. And today I'm going to focus on exponential ergodicity, and yesterday Tobias touched on response theory. Yeah, so let's have a look at the model. So the model is quasi-geostrophic model. This is what it's called, and it's usually used for capture the large-scale features of the atmosphere of the ocean at the mid-latitude, so our latitudes. And when we account for several layers, so different density, we can describe with this model also the density stratification of our fluid. And if we allow for different, is it all right? There are two. Should I turn one off?
Yes.
I'll turn it closer. Better? Yeah, but let me know. No, it's all right. Yes, I was saying that when we allow for density stratification, then there is a formation of these baroclinic instabilities. These are a mechanism that is behind the formation of major weather fronts and oceanic currents. So the model itself is very popular in meteorology and climatology because it strikes a balance between its simplicity and the amount of features that it can represent. So here there is a very schematic picture of two layers, and the quantities that we want to model are written over there. So there's psi1 and q1 and psi2 and qi2. And I'm going to tell you in a second what this q is, but psi is the stream function, so stream function of a fluid. Velocity is orthogonal gradient of the stream function. And again, just to reiterate, studying the ergodic properties of this model, why we want to do this, because we want to understand if the system stabilizes, in a sense, on average, and more specifically, with the configuration of the noise that we want to consider, we want to understand if injecting noise or injecting uncertainty on one layer is enough to stabilize also the other layer. So understanding what is actually the influence of a stochastic wind forcing on currents. For example, or the behavior in general of the entire ocean when you force only from the top. So this is it. This is the beast. No, it's very easy. So the stream function, again, here, psi. So we have two, and we are considering the torus. We can discuss later about the boundary conditions, what are the most physical to consider. But in general, periodic, at least in one direction, is very physical, especially for the atmosphere, but also for the ocean in certain configurations. And yeah, on the left-hand side, we have basically just a material derivative, if you don't consider now the stochastic parts. Material derivative of these quantities, Q, and when we consider forcings, we have everything on the right-hand side. So here we will have the influence of the rotation. Sometimes this comes directly in the definition of Q, but here it's separate. So this comes from the fact that we are on a rotating planet, so the Coriolis. Here, some viscosity that comes, of course, not from the molecular viscosity of the ocean, but from small vortices that we call eddy viscosity. And then on the bottom, we have some terms of drag, some friction that would come from the interaction with the boundary layer on the bottom of the ocean, for example. On the top, here we have a forcing. So deterministic forcing here, time independent for the time being. Actually, to do ergodic theory, we need that time independent. And then a white noise. So this is just a Wiener process, nice as you like, with a trace class covariance operator. And the quantity Q are related to psi in this way. So by a Laplacian and just a difference here, they can be accounted as a discretization of vertical derivative when you have a difference between layers. So it behaves pretty nicely in terms of psi, because it's just a linear operator of it, and it's like a Navier-Stokes, two copies of a Navier-Stokes equation in vorticity formulation stacked to each other and with some sort of interaction. So it will have the same good behavior. So this model is well posed as pathwise unique solutions and so on. And it has an invariant measure as well. But let me be more precise with what we mean by that. Let me just comment again that having the noise only on one of the two layers will make this noise effectively degenerate because it's acting only on half of the degrees of freedom, even if the noise itself could be full when it's on the first layer. Okay, so probably this is familiar to most of you, maybe not, so let's just recall it. The transition probabilities are effectively, if I have a solution of my model, I'm looking at what is the probability that if I start at Q0 at time t, I will end up in certain set. So this is what we call transition probabilities. And an invariant measure, it's going to be a distribution, so a measure that will not see the action effectively of my dynamic, so that it will preserve averages of observables. So when I talk about observables, there are functions that go from the space wherever I have solutions to R or whatever scalar. And if the invariant measure is unique, then it's going to be also ergodic. In our case, this is the definition that we use for exponential ergodicity, but it's widespread. So we are asking that there exists a constant that may depend on the initial condition, and a parameter gamma that doesn't necessarily. And then you have some sort of convergence of the transition probabilities to the invariant measure. So this is effectively exponential convergence of transition probabilities to the invariant measure. So what does it say? It says that when we start from any initial condition, at some point in the long run, I'm not gonna, in a sense, see my initial condition because the distribution is gonna be the same. It's gonna be the invariant measure here. And what is the distance? In which sense do we have this convergence? We have a Wasserstein distance, or more precisely, it should be a weaker sense, so a Wasserstein semi-distance. Okay. So we want to establish effectively a convergence of this type of transition probabilities. So let me jump to the result. So the result is that we can find a critical R0. I remind you, R is the parameter that we have on the friction, the interaction with the lower of the lower layer with the boundary layer or orography, something like this. And we do have this critical R, and if we take other bottom frictions that are larger than this R0, so in a sense large enough, and the noise that I mentioned before is acting on enough degrees of freedom, always on the first layer, but on enough degrees of freedom, then there exists a rho that is smaller than 1 and at positive times, so that for all the times greater than this T star, we have a sort of contraction of the transition probability. So if we start, say, from two different initial conditions, I know that this is, again, the Wasserstein distance associated to this distance here. I'm going to have a contraction here on the transition probabilities. And by iterative argument, this can be shown, of course, to imply the exponential ergodicity. So this result, too, actually implies also the spectral gap that yesterday Tobias Kuna was mentioning about as a necessary condition or one of the conditions that we require for linear response when we study these sort of models. So yes, this is effectively implying the exponential ergodicity and the spectral gap, but exponential ergodicity and spectral gap are not equivalent necessarily for some technical reasons here. Yeah, perfect. Okay. I'm going to talk to you a bit about the strategy, but this is very hand-wavingly, and if you want more details, I'm happy to discuss this later. So effectively, to try to show this, we want to apply what is called Harris theorem. And Harris theorem is what ensures what we showed before, and it was generalized for SPDs in this paper by Heider, Mattingly, and Schweitzer in 2011. And to apply this theorem effectively, what we have to do is to bound in an appropriate Wasserstein distance this quantity here. Okay, if we want to bound this, we have, in effect, to control this part, we have little wiggle room. We don't have a knob that we can actually play with, and so we really have to rely on the dynamic to show this. So the idea of instead of generalizing coupling, that here I cite to Bukowski, Kulik, and Shozov 2020, but there were several works also before that maybe called this method asymptotic coupling. Is all in that same, yeah, this is not an exhaustive list of references. So the idea was, what is it? Is to consider a second copy of the model with initial condition Q0 bar, for example. And in our context of this layered model, we consider the same structure in the second layer. So we maintain the second layer exactly the same in the second copy. And in the first layer instead, we consider not the same noise, but an equivalent noise. That is the original noise plus a control term. Just schematically, so we maintain the same equation, and then we have a term G here that would be our control. So, okay, now we have this function that we have to find and so on. So it seems more complicated, but say if D was a simple distance that in other cases it's not. So there are some technicalities to overcome. But if D is a distance, then we can consider, for example, by triangular inequality, this difference. So this is what we want to estimate. And here we plug in basically the same transition probabilities, but of this new function, of this new solution. And the same thing here, no? So here we would have the difference between the original version with the original initial condition of the new one with the different initial condition. And then effectively the same initial condition, but what's the difference from the one controlled, this one, and the original one. So now we have a knob to play with, no? So we have to find, we have a G, so we have a control that we can tune to bound this guy and this guy. So this is a strategy. Then of course, now the new version of the goal is to find such control. Find such control that is usually done by a priori bounds in a classical way. We can get the desired estimates for the right-hand side of the equation that we just looked at. Okay, so let me stress again that the control in our case has to act where the noise is. So it has to act only on the first layer, but can depend on both the layers, on the controlled one and the uncontrolled one. Okay, so in the results that I just presented to you before, we take G that depends only on the first layer, so it's effectively like a Laplacian of the difference. And so in this case, the control is helping stabilizing the first layer because it's actually, especially because it's not using the information of the second layer in it. So that's a bit the origin of this requirement that we have on the friction. So we are effectively asking for the second layer to be passive on its own via a large friction, and then the control is helping stabilizing the first layer instead. A new control of that is a work that we have in preparation. We are very confident that this new control that we found exploits a bit better the interaction between the layers that in this control we didn't. So because we want to basically try to push the action of the noise to the second layer, and how we want to do this if we're not exploiting the interaction between the layers. Okay. So with this new control, probably though, we will need some hyperdiffusivity. No conditions on parameters, but hyperdiffusivity. So a little bit more drag or diffusivity on the high modes at least. Okay, so just a summary and an outlook for now. So we looked at a model for large-scale circulation at the mid-latitudes. with two density layers, one of the two forced by a noise. We wanted to look at when the solution laws converge exponentially in distribution to the z-invariant measure, and a necessary condition of the model were imposed in one context, but there might be no conditions if we have hyperdiffusivity. Where to go from now? From here, so as I mentioned before, this is also a necessary condition for linear response, so studying the dependence of this invariant measure on the parameters. One question would be, can we do this with different boundary conditions? What are the difficulties that we might encounter? And then having this methodology having this methodology, we can try to apply it to different models. For example, an energy balance model or a 1D compressible Navier-Stokes. This is what we're working at the moment. And if we have other forms of noise, well, of course, ergodicity and all this framework cannot be used, but can we still retain something on stationary solutions, for example? And this is a work that recently did with Eliseo Luongo, where we use a transport noise and try to see that you have convergence to stationary solutions instead. Yeah, that's all I wanted to tell you. Here are some references, and thank you very much.
Thank you. There are questions? Okay. If there are no questions, we thank again the speaker.